Hey all, we are on to the second concept of the similar triangles unit, and here we're going to talk about how to show or prove that triangles are similar, and we're going to talk about some theorems and postulates. So just as a reminder from similar polygons, the same rules apply for similar triangles with similar polygons. Corresponding angles are congruent, and the ratios of the corresponding sides are in proportion. So this is kind of a repeat, just a reminder from 6.1 similar polygons. The first way we can show that two triangles are similar is if we have two pairs of corresponding angles, and that's called the angle-angle similarity postulate. Remember that a postulate is something that we accept to be true. So here's that in writing. Two pairs of corresponding angles in two triangles are congruent, and the triangles are similar. So if we look at these two triangles over here, we see that angle C is congruent to angle D, and angle B is congruent to angle E. And there's that in writing. So we have two pairs of corresponding angles congruent to each other in these two triangles. So we don't have to check anything else about these triangles. We can say that they're similar by the angle-angle similarity postulate. You can see how easy it is to confuse calling triangles congruent and similar, as I've just done it twice. So make sure that you are careful about what you're writing about these two triangles. So these two triangles are similar, and we can write a similarity statement that triangle ABC is similar to triangle FED. And just like a congruent statement, that is a similarity statement about the two triangles. And remember, that's the symbol for similar. Here we have a theorem, which means that somebody somewhere proved that this is true. The side-side-side similarity theorem. This is how we shorten it, SSS, with the similarity symbol. And you might have guessed that this is going to talk about three pairs of corresponding sides. So if we have all three pairs of corresponding sides in two triangles in proportion, that means their ratios are equal, then we can say that the triangles are similar, and we don't have to know anything about the angles. So here are the three pairs of corresponding sides written in proportion. The length of AC over the length of DF is equal to the length of AB over the length of EF, which is equal to the length of BC over the length of DE. And we'll write that using the actual lengths. And we can see that all three of these ratios are equal. They all simplify to be 2 over 1. And just as a reminder, that 2 over 1 is the scale factor. That means that each side in ABC is twice as big as their corresponding sides in the other triangle. So again, we have triangle ABC similar to triangle FED. And you can write that similarity statement if you like. We have one more way to show that triangles are similar. It's the side-angle-side similarity theorem. Again, a theorem, something somewhere somebody proved to be true. So here we're going to have two pairs of sides and the included angles. The included angle means that the angle is between the two sides that we're using. So we can see here in this triangle that angle B is between AB and BC, which are the two sides that we're going to use as our corresponding pairs. Same thing over here. angle E is between EF and DE. This angle is formed by the two sides. So that's an important piece here when we're doing side angle side. There's the theorem. So we have two pairs of corresponding sides in proportion, and the included angle is congruent. Then we can say the triangles are similar. So from the picture we know that angle B is congruent to angle E. And we'll need the length of AB over the length of EF to be equal to the length of BC over the length of DE. And if we take those values for the lengths and we put them in ratios, we can see that they are equal. They both simplify 18 over 12, 21 over 14, both simplify to 3 over 2. So they are in proportion. Remember, again, that's the scale factor, 3 over 2. So we can say that these two triangles are similar by the side angle side similarity theorem. And you can just write SAS with the similar symbol. So a little less than proving triangles congruent, we have 3 postulates and theorems this time instead of 5. So we only have 3 choices to make if we think 2 triangles are similar. Pause the video here and determine if each pair of triangles are similar, and then if they are, state by which theorem, and then write the similarity statement, the triangle similarity statement. I recommend, as we did in polygons, checking angles first. If we don't have any angles congruent, we still can check the sides and proceed from there. So go ahead and pause and try these 2 examples. So if we look at this first one, these 2 triangles, we don't see any information about the angles. So if we're trying to check off angles, we can see that we don't know anything about them being congruent. So our only option here is to see if all the sides are in proportion, and then we can use side, side, side. So let's check that. We'll write the proportions of the corresponding sides. Now we need to see if they all simplify to be the same fraction, and they do. They all simplify to be 1 over 6. So all 3 pairs of corresponding sides are in proportion. And again, as a reminder, 1 over 6 represents the scale factor. So since we have all 3 pairs of sides in proportion, they're all equal to the same fraction, then we can say that these 2 triangles are similar by side, side, side. Something happened here. So these are similar by side, side, side similarity. In my similarity statement, triangle ABC is similar to triangle HGF. I had this all set up nicely for you, but something got erased. Let's move on to this example. It's a little more difficult. We have 2 triangles in here, but it might be hard to see. I always recommend maybe drawing these triangles separate from each other. I have triangle KBC, and I have triangle KLM. Both triangles share angle K, so that means that angle K is going to be congruent in both triangles. That's the reflexive property. We've used the reflexive property just for sides, but now we can use it for angles. It's the same idea. So when we're checking angles, we can see that angle K is congruent to angle K. We don't know anything about any of the other angles, so now the only option we have here is to show these 2 triangles similar by side angle side if the sides are in proportion. So let's check the sides that we know. KB in the small triangle corresponds to KL in the big triangle. KC in the small triangle corresponds to KM in the big triangle. So we need those two corresponding sides to be in proportion, so let's check if they are. 16, which is the length of KB, over 88, which is the length of KL. KC is 25. KM is 25 plus 107. You have to add these two segments together to get the whole thing. That's 132. Now these don't seem like simple fractions to simplify or reduce, so let's take a little bit of a shortcut and let's see if each of these is the same decimal. If you pop that in your calculator, you'll see that they are not. They're pretty close. 1.18 repeating, 0.189. They're pretty close, but they are not equal, so those pairs of sides are not in proportion. So we can say that these two triangles are not similar. So as always, I want you to try these two examples. Determine if each pair of the triangles are similar. If they are similar, tell me by which theorem or postulate. So angle, angle, side, 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 or side, angle, side. And again, if they are similar, I want you to write the triangle similarity statement. So use the information you got from this lesson, try these two problems, and we'll discuss them in class.